Hi everyone, so in this video we are going to discuss all the methods to check whether a given number is prime number or not. So we'll discuss 5 methods. Before discussing any of the methods, let's see what is the prime number. So let's say 1. Okay, so 1 is divided by 1, so it has 1 divisors, which means it is not a prime number. Let's see 2. So 2 has 2 divisors, 1 and 2. So it is a prime number. Let's say 3, it has 1 and 3, it is a prime number. So let's say 4, so it has 1, 2 and 4 as divisors, it is not a prime number. So a number is a prime number if it has only 2 divisors. So if a number has less than 2 or greater than 2, then the number is not a prime number. So now we know what is a prime number. Now let's see the first method. So in first method, it's the quite naive method. So we'll start with 1 all the way up to x, and we divide the given number x by all the numbers, and we'll see at the end what is the total count of divisors we found until now. So if the count of total divisors is equal to 2, then it is a prime number, and if it is not equal to 2, then it is not a prime number, right? So let's implement this and see. So we'll have count of divisors initially 0. Now we'll start with 1. I is less than equal to n and I plus plus, and if n divisible by I, then we'll increase count of div, and finally we'll check if count of this divisors is equal to 2, then it is a prime number, else it is not a prime number. So our base case has been passed, and now we'll submit to check whether it can pass all the test case or not. So all the test case has been passed. So in this we traveled from 1 to x. So the time complexity of this will be big of n, and since we didn't use any extra space, the space complexity will be big of 1. Now let's see method 2. So in method 1 we used 1 all the way up to x. Now we know 1 and x are already the divisor of a given number, right? So we can exclude these. These are the two divisors we have. Now what we have to check is from 2 until x minus 1. If we find any divisors here, then we can say that it is not a prime number, because a prime number has only 2 divisors, right? That is 1 and the number itself. We already have that. Now the numbers left are 2 to x minus 1, and if we found any number in this range that can divide x, then it is not a prime number, else it is a prime number. Now let's see this approach. So we'll start with 2 all the way up to n minus 1, and if any number divides in this range, then we can say that it is not a prime number, and if we came out of the loop without returning, then it is a prime number. But if a number is less than or equal to 1, number is less than or equal to 1, it is not a prime number. So for 1 it will return false. For 2 is less than equal to 1, so for loop will not run and it will return 2. So for 3, I is 2, I is less than equal to 2, so the for loop will run but it will not return. So on exit it will return true. So it will check for all the numbers, and if the number n is divisible by any number in the range 2 to n minus 1, then we can say that it is not a prime number, else it is a prime number. So our base case has been passed. Now we'll submit to check whether all the test cases are being passed or not, and all the test cases has been passed. So the time complexity of this algorithm is also big of n, because although we rejected or we separated out 1 and the number itself, but we still checked for all the number from 2 to x. But you would ask why big of n? Because when we found any divisors, for example here, we exit early and say false. But in worst case, if a given number is a prime number, then none of the number from 2 to x minus 1 can divide x, right? So in that case we traveled all the way from 1 to x. So that's why the time complexity is big of 1 and the space complexity is still big of 1. Now let's see method 3. So in method 2 we use the sample space of 2 to x minus 1, right? Now what I'm saying is, you take any number, you cannot divide the number x by any number greater than x by 2 but less than x. less than x but greater than x by 2. So let's say 25. Half of it is 12.5. So 13, up until 13 to 24. You will not find a number in range of 13 to 25 that can divide 25. So you cannot divide a number by greater than half of it and less than the number, right? So we can check from 2 to x by 2, and if we find any number in this range that can divide x, then we can say then that it is not a prime number, right? So let's implement this algorithm as well. So we'll check for n is less than equal to 1, return false. From 2 to n by 2, if any number that can divide n, then we'll return false, else we'll return true. So our base case has been passed, and now we'll submit to check whether it can pass all the test case or not. And all the test case has been passed, and the time complexity of this algorithm is still big of n, right? So even though we have reduced the sample space from 2 to x by 2, so it is big of n by 2, which is still big of n, and the space complexity is big of 1. Now let's discuss algorithm 4. So we reached to a sampling of 2 to x by 2, right? Now let's see this. We have, let's say, a cross b is x. Now I can say that one of the root is x or other root is also x, which gives x. One of the root is less than root x, one of the root is greater than root x, one of the root is less than, other root is also less than, one of the root is greater than, other root is also greater than, one of the root is greater than, and other of the root is less than. Now if both the roots are root x, then we will get multiplication equal to x. If one of the root is less than root x and other is greater than root x, then their multiplication might lead to x, right? This also right, this also right. Now if one of the root is less than root x and other is also less than root x, then it can never form x, right? If one of them is greater than root x, other is also greater than root x, then their multiplication will always lead to something that is greater than x, right? So this is also wrong. If one is greater than, other is less than, then it can form x, right? Perfect x, right? So we are left with three equations, that is either root x gives x, or root x that is less than root x, and other root that is greater than root x gives x, or one of the root is greater than root x and one of the root is less than root x gives x. Now what I mean by this is that we have sample space of 2 to x by 2, and let's say here is root x. So either both the root are root x, one of the root is less than root x and one of the root is greater than root x. One of the root is greater than root x or equal to root x. So it's one of the root is less than equal to root x and other is greater than equal to root x. One of the root is greater than equal to root x and other is less than equal to root x, right? So these are the form. Now for a number to be a prime number, the number should have only two divisors, that is 1 and the number itself. Now if we find any divisors in between that, then we can say that it is not a prime number, right? So we can check only this portion, right? So if we find one divisor on or before root x, then we can say that count of divisors is greater than 2 for this, and this cannot be a prime number. So let's see. We'll start with 2, and I multiply I is less than equal to n, which is basically I is less than equal to root of n, right? I plus plus. Now if any number can divide n, then it is not a prime number, else it is a prime number. So our base case has been passed, and now we'll submit this. So all the test case has been passed. So the time complexity of this algorithm is big of root of x. That is, we checked for a sample of 2 to root of x only. Now the next method. So next method is basically optimizations over the. So when we have done method 2, it was optimized over method 1, 3 over 2. And method 4 was optimization over method 3. Now this last method is optimization over method 4. So our sample space is 2 to root x. How can we optimize this? Now listen carefully. Any integer can be represented in the form of 6k plus 0, 6k plus 1, 6k plus 2, 6k plus 3, 6k plus 4, 6k plus 5. So if number is less than or equal to 1, it is not a prime number. You know why? Because 1 is not a prime number. If number itself is 2 or 3, it is a prime number. Now the important step. If number is divisible by 2 or 3, it is not a prime number and we exit. Right? If number is divisible by 2 and 3, we exit. Because if number is 2 and 3, that is fine, it is a prime number. But because if number is not 2 and 3, it is some other number which is divisible by 2 and 3, then it is not a prime number. We can exit. Count of divisors is greater than 2 here. Now from this point onwards, if we are at this point, which means that the number is not divisible by 2 and 3, right? Now here's the important thing. If number is not divisible by 2 and 3, we don't have to check for those numbers, right? For example, if we check this number, right? So what we were doing up until now, we were dividing all the number from 2, 3, 4 until root x. So we were dividing these number to x to check whether they can divide x or not. And if any number can divide x, then it is not a prime number, right? So my point is, if any integer can be represented in this form, and this is one of the integer, and we are at this point. By this point I mean that n is not divisible by 2 and 3. Okay, so now this is the number 6k plus 4, which is nothing but 2 multiply 3k plus 2, right? This is multiple of 2. Now what we have to do? We have to do this x by 6k plus 4, which is x by this. Now we just said that this x is not divisible by 2 at this point. We are at this point, right? So x is not divisible by 2. It might be divisible by 3k plus 2. I am not saying, but x is never divisible by 2, which means x is not divisible by 6k plus 4, which means checking for these number is useless because they never divide the given x, right? Similarly, we checked for 3. So 6k plus 3 is nothing but 3 2k plus 1, and we above said that x is not divisible by 3. So x is not divisible by 3. It might be divisible by 2k plus 1, I don't know, but it is not divisible by 3, which means it is not divisible by 6k plus 3. So any number of the form 6k plus 3 is also useless. Since the 6k plus 3 numbers cannot divide x, we don't have to check for that, right? Similarly 6k plus 2, these are 2 3k plus 1 form 2, we can erase that. Then 6k plus 0, we can cut that. So we are left with 6k plus 1 and 6k plus 5. So these two terms, 6k plus 1 and 6k plus 5, these are the only two terms that we have to check. Rest all of the terms has been crossed out, because if n is divisible by 2 and 3, we know that it is not a prime number and we exit. But if we are at this point, n is not divisible by 2 and 3. N is not divisible by 2 and 3 means that these numbers, these numbers are of no use. We don't have to check for these numbers. We are left with only terms of these forms 6k plus 1 and 6k plus 5. They might divide number x. We are not sure. So we have to check for those numbers, right? So what are these terms that we have to check for? 6k plus 1. Okay, now 6k plus 5 can be written as 6k plus 6 minus 1. 6 of that is k plus 1 minus 1, that is nothing but, let's say, 6k minus 1. So these are two terms, 6k plus 1 and 6k minus 1, right? Now you might say 6k plus 1 or 6 minus 1 may be the terms that are prime number, because 5, that is 6k, k is 1 minus 1, 5. Okay, yes, it is prime. Let's say 7, that is 6k plus 1, k is 1, it will give 7. But 25, so it is 5 multiply 5. It is not a prime number, right? But it is of the form 6k is 4, plus 1, that is 6k plus 4, it is k is 4, right? So if a number is of the form 6k plus 1 or 6k minus 1, it is not necessarily a prime number, right? The only thing that I am telling you is that 6k plus 1 and 6k minus 1 out of the range 2 to root x, in this range these numbers can still divide x. That's what I am saying. So if these two ranges 6k minus 1 and 6k plus 1 can divide x, now we have to check only for those numbers. So we'll start with, let's say, 2 to root x. We checked for 2 and 3 separately, right? We checked first here only. So we checked that x is divisible by 2 and 3. We checked, right? And for less than 1 also we checked. We are left with 4 to root x. Now 4 is of the form, that is 6k plus 4. K is 0. So this is this term. So we will not include 4 because we already rejected this. Now next term is 5. That is of the form 6k minus 1. So we'll start with 5. So we'll start with 5 and I is less than equal to root of x, I plus equal to 6. Why 6? I'll let you know. Now we have to check for 6k plus 1 and 6k minus 1. And 5 is of the form 6k minus 1, right? It is of the form 6k minus 1. So we will divide x by I. So this is I. So by dividing x by I, we are dividing x by 6k minus 1. And we will divide x by I plus 2. By that we will be dividing x by 6k plus 1. So let's see this. So we have x divided by what? 5. Then we will divide x by 7, right? Then for the next iteration we will increment by 6. So I is 5 plus 6, that is 11. Then we will divide x by 11. Then we will divide x by 11 plus 2, 13, right? So let's just take an example. Let's say 25. What is root of 25? Root x, that is 5. So we'll start with 5 and over at it. So we'll start with 5. I is less than equal to root x. So I is less than equal to root x, that is 5. And I plus equal to 6. So it will iterate only one time. So we will divide x by 5 and it divides, will return false. It is not a prime number. And then we don't have to check for x is I plus 2 form because here only it returned false. So let's just implement this algorithm, and maybe while writing the code you might understand it better. So for less than equal to 1 we already did. We'll check if the number itself is 2 or 3. So n is less than equal to 3, which means return true. They are prime number. Then we'll check if a number n is divisible by 2 or n is divisible by 3. In this case we will return it is not a prime number. Now if a number is not divisible by 2 and 3, we'll check for, start with 5. Same condition, I is less than equal to root n. Will increment by 6 and we'll check if n divides I or n divides I plus 2. Then it is not a prime number, else it is a prime number. Now let's see if this works or not. So our base case has been passed, and now we'll submit this. And all of our test case has been passed. So for this algorithm also, the time complexity is big of root of x and space complexity is big of 1. So method 5 is just the improvement over method 4. So this is all about all the methods. If you didn't understand about any methods, just go over the video again and again. The only thing about all these methods is that in the method 5, the only thing that might confuse you is the point about these, that why we ignored these terms 6k plus 0, 6k plus 2, 6k plus 3, 6k plus 4. why we ignored this, and you'll have to watch the video again to understand it. The link is with this term, okay, with this term and these terms, why we ignored these terms. Okay, so to understand it better, just take any larger example. We took an example of 25, so the for loop ran only one time. Okay, so you might take a larger number, maybe a prime number or a non-prime number, and then do the iterations yourselves. Just do the manual work and you will understand the method better.